In this video, we are going to learn to calculate number average degree of polymerization from extent of reaction. Calculate the number average degree of polymerization of an equimolar mixture of adipic acid and hexamethylene diamine for the following extents of reactions: 0.1, 0.3, 0.5, 0.8, 0.9, 0.9995, 0.97, 0.99, and 0.995. Plot a graph of number average degree of polymerization xn versus p. What is the nature of the graph? We start off by first writing the formula 1 over 1 minus p equals xn, where xn is the number average degree of polymerization and p is the extent of reaction. Plugging in the values, we get 1 over 1 minus 0.1 is 1.11, 1 over 1 minus 0.3 is 1.43, 1 over 1 minus 0.5 is 2, 1 over 1 minus 0.8 is 5, 1 over 1 minus 0.9 is 10, 1 over 1 minus 0.95 is 20, 1 over 1 minus 0.97 is 33.33, 1 over 1 minus 0.99 is 100, and 1 over 1 minus 0.995 is 200. Now we plot a graph of xn versus p, and we see that the degree of polymerization increases slowly first, and then towards when p tends to 1, it rises very fast. So the graph of p versus xn is exponential. A polyesterification reaction that has an equilibrium constant of 16 is carried out between 5 molar carboxyl group and 5 molar hydroxyl group concentration in a closed system. What would be the degree of polymerization, and to what extent will the reaction proceed? What is the concentration of water in the system? If the same reaction is carried out in an open driven system, what should the concentration of water be brought down to so that we could obtain a degree of polymerization of 50? Let's write down the initial concentrations. Initially, we have 5 molar of acid, 5 molar of alcohol, and 0 of the polymer and the water. At equilibrium, if P is the extent of reaction, then 5 minus 5P would be the concentration of the acid, and 5 minus 5P would be the concentration of alcohol, and 5P of polymer would be formed, and 5P of water would be formed. So plugging this value, we get K equals 5P times 5P over 5 minus 5P the whole square. This gives us P over 1 minus P squared. So we can see that the equilibrium constant is independent of the initial concentration. Rearranging for P, we get P is equal to square root of K over 1 plus square root of K. Since K is given as 16, P would be square root of 16 over 1 plus square root of 16, which is equal to 4 over 1 plus 4, or 4 over 5. So the value of P is 0.8. Now, if we know P, we can calculate Xn. Xn equals 1 over 1 minus P. So which is equal to 1 over 1 minus 0.8, 1 over 0.2, which is 5. So the degree of polymerization is 5. N0 times P. So that would be 5 times 0.8, which is 4. So that's the equilibrium concentration of water. So this is the first part. The second part is in an open driven system. The degree of polymerization is given as 50. So the extent of reaction is xn equals 1 over 1 minus p. Plugging this, we get 50p is equal to 49. So p equals 49 over 50, which is 0.98. So the extent of reaction is 98%. Now, knowing the extent of reaction, now we can find out the quantity of water that should be present so that we can get this degree of polymerization. Coming back to the equilibrium constant, which is given as 16, is equal to 5p times the concentration of water over 5 minus 5p the whole square. Now p is 0.98, so we can plug that value. 5 minus 5 times 0.98, that square. Solving for the concentration of water, we get 0.0326. So the concentration of water in an open driven system should be brought down to 0.0326 so that we can get a degree of polymerization of 50. Derive the rate expression for the polymerization of stoichiometric amounts of hexamethylene diamine and adipic acid. We start off by writing the equation for hexamethylene diamine and adipic acid condensing with the elimination of water. Let us look at the mechanism. Carboxylic acid from one adipic acid molecule acts as a proton donor and protonates the carbonyl oxygen of the other adipic acid molecule. This is step 1. In step 2, the nucleophilic amino group attacks the carbonyl carbon of the protonated group. This is followed by the elimination of water molecule and the proton is released. Thus, one molecule of the diacid acts as a reactant and the other molecule of diacid acts as a catalyst. The reaction is second order with respect to carboxylic group due to its dependence on the diacid as a catalyst and as a reactant. The reaction is first order with respect to the diamine. The rate expression can be written as rate equals carboxylic group to the power 2 and amino group to the power 1. For a stoichiometric ratio of carboxylic to amino group being 1:1, rate can be written as rate equals to m cube, where carboxylic group concentration equal to amino group concentration equal to m. So the rate expression can be written as dm over m cube equal to kt, where k is a rate constant. Integrating this, we get 1 over m squared minus 1 over m0 squared equal to 2 kt, where m0 is the initial concentration at time t equal to 0. If p is the extent of reaction, then m equals m0 minus m0p. Substituting for m, we get 1 over 1 minus p the whole squared equals 2m0 squared kt plus 1. This is the rate expression. In this video, we are going to study how to determine gel point in step polymerization using Carother's equation. Determine the gel point or extent of reaction at which gelation occurs using Carother's equation for the various ratios of reactants below. Stoichiometric amounts of phthalic anhydride and glycerol. Phthalic anhydride and glycerol in the ratio 1.5 is to 0.95. Phthalic anhydride, glycerol and ethylene glycol in the ratio 1.5 is to 0.8 is to 0.15. And phthalic anhydride, glycerol and ethylene glycol in the ratio 1.5 is to 0.5 is to 0.8. What is the effect of non-stoichiometric quantities or functional groups on the gel point? We start off by first writing the structures of phthalic anhydride and glycerol. Phthalic anhydride is an anhydride of phthalic acid and it has two carboxyl groups. Glycerol has three hydroxy groups. So let's find out the stoichiometric ratios of phthalic anhydride and glycerol. We need 3 moles of phthalic anhydride to give 3 times 2, 6 carboxylic acid to match 2 moles of glycerol to give 2 times 3, 6 moles of hydroxy. So the stoichiometric ratio of phthalic anhydride to glycerol is 3:2. Now let's calculate the F average. The average functional groups is 3 times 2 of phthalic anhydride plus 2 times 3 of glycerol divided by the total number of molecules. This divided by 3 plus 2, which is the total number of molecules, and we get that equal to 12 over 5, which is 2.4. Now from Carother's equation, PC is equal to 2 over F average, so that's 2 over 2.4, which is 0.833. So this is the PC value for stoichiometric ratios of phthalic anhydride and glycerol. Now next, part B. The ratio of phthalic anhydride to glycerol is 1.5 to 0.95. Now let's calculate the total number of functional groups. We have 2 carboxylic acid groups in phthalic anhydride, so 1.5 times 2 is 3.0. And we have 3 hydroxy groups in glycerol, so 0.95 times 3, which is equal to 2.85. Okay, so 3.0 is greater than 2.85. So phthalic anhydride is in excess and glycerol is the deficient molecule. We have to find F average, and F average is defined as twice sigma of NiFi for the deficient functional group divided by total number of molecules. So which is twice of 2.85 in this case, divided by 1.5 plus 0.95. Which is 5.7 over 2.45. And so the F average is 2.327. Now plugging this into the Carother's equation, we get 2 over 2.327, which is 0.8595. So note that when the ratio is non-stoichiometric, the value of PC is higher than that for stoichiometric ratio of 0.833. Now part C, we have phthalic anhydride, glycerol and ethylene glycol in the ratios 1.5, 0.8 and 0.15. Let's again calculate the total functional groups. 2 carboxylic acid groups for phthalic anhydride, so 1.5 times 2 is 3.0. 3 hydroxyl groups for glycerol, so 3 times 0.8 is 2.4. And 2 hydroxyl groups for ethylene, so 0.15 times 2 is 0.3. So the total number of hydroxyl groups is 2.4 plus 0.3, which is 2.7. which is less than the amount of carboxyl acid groups, which is 3.0. So the hydroxyl group is in deficient and the carboxylic acid group is in excess. So while finding F average, we are going to use the hydroxyl group. So F average is 2 times sigma Ni Fi of the deficient functional group over total number of molecules. So this is going to be 2 times 2.7 divided by 1.5 plus 0.8 plus 0.15. That gives us 5.4 over 2.45. So F average is equal to 2.2041, and plugging this into PC equals 2 over F average, we get 2 over 2.2041, which is 0.9074. Okay. So you can see how PC is again higher for non-stoichiometric than for the stoichiometric value of 0.833. Okay, part D. We have phthalic anhydride, glycerol, and ethylene glycol in the ratio 1.5 is to 0.5 is to 0.8. So let's again calculate the total functional groups. Phthalic anhydride is going to be 1.5 times 2 carboxylic acid groups, which is 3.0. Glycerol is going to be 0.5 times 3 hydroxyl groups, which is 1.5. And ethylene glycol is 0.8 times 2, which is 1.6. So we have a total hydroxyl group or quantity of 1.5 plus 1.6, which is 3.1, which is greater than the quantity of carboxyl groups, which is 3.0. So the functional group that is in deficient in this case is the carboxylic acid group. So for finding the F average, we are going to use the carboxylic acid group concentration. So again, F average is twice of sigma Ni Fi over sigma Ni. So 2 times 3.0 divided by the total number of molecules, which is 1.5 plus 0.5 plus 0.8. And that is 6.0 divided by 2.8, which is 2.1429. So PC is 2 over F average, which is 2 over 2.1429, which is 0.933. So once again, the PC value for non-stoichiometry is higher than that for stoichiometric concentrations. This is because for non-stoichiometric concentrations, only the molecule that is in deficient quantity is contributing to the cross-linking. So the degree of polymerization decreases with non-stoichiometry. In this video, we are going to determine gel point and step polymerization using Flory-Stockmeyer statistical approach. Determine the gel point extent of reaction at which gelation occurs using Flory-Stockmeyer statistical approach for the various ratios of reactants below. Phthalic anhydride and glycerol in the ratio 1.5 is to 0.95. Phthalic anhydride, glycerol and ethylene glycol in the ratio 1.5 is to 0.8 is to 0.15. Phthalic anhydride, glycerol and ethylene glycol in the ratio 1.5 is to 0.5 is to 0.8. So Flory-Stockmeyer equation is here. 1 over square root of R times FWA minus 1 times FWB minus 1, where R is the feed ratio and R is less than 1, and FWA and FWB are the weight averages of the functionalities A and B. Now, in the first case, we have phthalic anhydride and glycerol in the ratio 1.5 is to 0.95. So, let's first try to find out the feed ratio. Phthalic anhydride has 2 carboxylic acid, so the functionality is 1.5 times 2, which is 3. Glycerol has 3 hydroxyl groups, so the functionality is 0.95 times 2 times 3, which is 2.85. So since 3 is greater than 2.85, for finding R, we want to put 3 in the denominator because R has to be less than 1, and 2.85 in the numerator. So we get the feed ratio as 0.95. Now let's find out the functionalities. The functionality of carboxylic group is, the weight average functionality of carboxylic group would be 1.5, which is its number of moles, times 2 squared because there are 2 carboxyl groups, over 1.5 times 2. Similarly, the weight average functionality of hydroxyl group is going to be 0.95 times 3 squared divided by 0.95 times 3. Okay. So if we do the calculation, we get the functionality of carboxylic group to be 2 and the functionality of OH group to be 3. Plugging this into the Stoichiometric's equation, we get Pc equals 1 over square root of R, which is 0.95, times 2 minus 1 times 3 minus 1. And that gives us a Pc value of 0.7071. Moving to the next part, we have phthalic anhydride, glycerol and ethylene glycol in the ratio 1.5 is to 0.8 is to 0.15. So let's find out the functionalities. For phthalic anhydride, that would be 1.5 times 2 carboxylic acids, which would be 3. For glycerol, it would be 0.8 times 3 hydroxy groups, which would be 2.4. For ethylene glycol, it would be 0.15 times 2 hydroxyl groups, and that would be 0.3. So the total hydroxy group is 2.4 plus 0.3, which is 2.7. So again, the carboxyl group functionality is more than the hydroxyl group functionality. So for finding the feed ratio, we are going to say R equals 2.7 over 3, which is 0.9. Now let's find out the functionalities, weight average functionalities of the carboxyl group. So FW of carboxyl group is 1.5 times 2 squared over 1.5 times 2. So this gives us 2. Weight average functionality of hydroxyl group is 0.8 times 3 squared plus 0.15 times 2 squared divided by 0.8 times 3 times 0.15 times 2. So this is going to give us 2.89. To find PC, PC equals 1 over square root of R, which is 0.9, times 2 minus 1 for the carboxylic group and 2.89 minus 1 for the hydroxy group. And PC comes to 0.7667. Now, the last part. Here, the ratios of phthalic anhydride, glycerol, and ethylene glycol are 1.5 is to 0.8 is to 0.5. So the functionalities are for phthalic anhydride 1.5 times 2, which is 3. For glycerol, it is 0.8 times 3, which is 2.4. And for ethylene glycol, 0.5 times 1, which is 0.5. So the total hydroxy functionality is 2.4 plus 0.5, which is 2.9, and the carboxyl functionality is 3.0. So we have carboxyl functionality in excess, and that would be in the denominator for finding the feed ratio. So the feed ratio would be 2.9 over 3.0, which is So for finding the feed ratio, we are going to say R equals 2.7 over 3, which is 0.9. Now let's find out the weight average functionalities of the carboxylic group. That would be 1.5 times 2 square over 1.5 times 2, which is 2. And the weight average functionality for the hydroxyl group would be 0.8 times 3 squared plus 0.15 times 2 squared over 0.8 times 3 plus 0.15 times 2, 2.89. So PC equals 1 over square root of R, which is 0.9, times 2 minus 1 times 2.89 minus 1. That gives us PC equals 0.7667. So the ratios of phthalic anhydride to glycerol to ethylene glycol is 1.5 to 0.8 to 0.5. Again, let's find out the functionality. For carboxylic group, it will be 1.5 times 2, which is 3. For glycerol, it will be 0.8 times 3, which is 2.4. And for ethylene glycol, it will be 0.5 times 2, which is 1. So the total hydroxy functionality is 2.4 plus 1, which is 3.4, and the carboxyl functionality is 3, so 3 is less than 3.4. So when we find R, we want to have the carboxyl functionality in the numerator and the hydroxyl functionality in the denominator, and we get a value of 3 over 3.4, which is 0.8824. Now let's find the weighted average functionalities. For carboxylic group, it would be 1.5 times 2 squared over 1.5 times 2. And for the hydroxyl group, it would be 0.8 times 3 squared plus 0.5 times 2 squared over 0.8 times 3 plus 0.5 times 2. So if we do the calculation, for carboxylic group, we get the weighted average is 2, and for the hydroxy group, the weighted average is 2.706. Plugging this into the Stoichiometric equation, we get 1 over square root of R, which is 0.8824, times 2 minus 1 times 2.706 minus 1. This gives us a PC value of 0.8150. So we have found out the PC value. Calculate the proportion of benzoic acid that should be added to equimolar quantities of adipic acid and hexamethylene diamine to produce a polymer of 10,000 molecular weight at 99.5% conversion. Let Na be the number of moles of diamine and Nb be the number of moles of diacid. Let Nb prime be the number of moles of benzoic acid, which is a monofunctional acid. Feed ratio is given as total amine functionality over total acid functionality. Feed ratio should be less than 1, so we want to have the amine functionality in the numerator and the acid functionality in the denominator. Feed ratio is given as Na over Nb plus 2 Nb prime. Since Na and Nb are equimolar, let us assume Na is equal to Nb is equal to 1. So R is equal to 1 over 1 plus 2 Nb prime. Xn is the degree of polymerization, and Xn is Mn over M0, where Mn is the number average molecular weight and M0 is the weight of the monomer. Mn is given as 10,000. Let us find M0. We have hexamethylene diamine and adipic acid eliminating water molecule to form the polymer chain. M0, the mass of the monomer, is given as half molar mass of the repeating structural unit plus half molar mass of water. This comes to 132 grams per mole. Now Xn is equal to Mn over M0, so it's 10,000 over 132, which is 75.76. Degree of polymerization is also given as 1 plus R over 1 plus R minus 2PR, where R is the extent of reaction. Extent of reaction is 0.995, so plugging this, we get R is equal to 0.9832. Nb prime is equal to 1 minus 0.9832 over 0.9832 times 2, so Nb prime is 0.0085 moles. So the ratio of diamine to diacid to benzoic acid is 1:1:0.0085.